In this video, we will discuss tension. Tension is the force exerted by strings or cords or rods when something is hanging from them or when they're being pulled. Now generally, to make our lives easier, we will think of the string that this box is hanging from. The box has a certain mass. We'll think of the string
Mr. Bergman, call the office.
as massless. If the string had mass, then something different happens, and we'll discuss that at another time. When the string is massless, I can think of the tension as being the same everywhere throughout that string. So if I were to look at a free body diagram of just the mass, I would have the force of gravity pulling down, which is mg, and tension holding it up. And I would know that those two forces would have to be equal if this object were at rest, since the net force is zero when the acceleration is zero. Tension tends to confuse people when it is part of a system. However, we'll see that we can make tension the same as the interacting forces of Newton's third law by way of an example. So in this example, I have a frictionless surface and three blocks, A, B, and C, being pulled to the right with a force of 6 newtons. The mass of A is 3 kilograms, the mass of B 2 kilograms, and the mass of C is 1 kilogram. Now you can see that the way that these will move is with the chords in between them being taut. And so there will be a tension in chord AB, there will be a tension in chord BC. And the kind of question I could ask you is, what is that tension? So what is the value of the tension in AB, and what is the value of the tension in BC when I'm pulling with 6 newtons? The general misconception here is that if I pull with 6 newtons of force, then these all have to equal 6 newtons. However, we'll see in just a second that that is an incorrect way to think about this. Just as with the multiple blocks being pushed, when you have multiple blocks being pulled, you need to think of the system first and then look at the parts. So let's look at the system. We've got 3 blocks being pulled, and if I think of those as one object, that object will have a mass of 6 kilograms, remembering that these were 3, 2, and 1. The net force on that, since the tension everywhere in this is the same and the tension everywhere in this is the same, the tension pulling on 3 and pulling on 2, pulling on 2 and pulling on 1 will cancel each other out. So those all cancel. The net force then ends up being just the 6 Newton force that I'm pulling on the entire system. With that, it's pretty easy to see that the acceleration, always net force over mass, Newton's second law, is 6 divided by 6, or 1 meter per second squared. Once we have the system acceleration, the other pieces fall into place pretty easily, since that system acceleration also is shared with block A and block B and block C. So all of these have to be accelerating the same, 1 meter per second squared. They each have a different mass, however. The mass of A, we said, was 3 kilograms. The mass of B was 2 kilograms. And the mass of C was 1 kilogram. Using that, we can figure out the net force on each block as m times A. in this case 3 newtons, in this case 2 newtons, and in this case 1 newton. If we now look at the individual free body diagrams of each block, knowing what the net force is, we can figure out what the tension is. The only force on block A is the 3 newtons, and that force must be coming from the tension in chord AB. For block B, there's tension in AB pulling back, and tension in BC pulling forward. Notice that those are not equal. BC is bigger than AB, meaning the block will move to the right. We know that the net force is 2, and we know that the tension in AB is 3, having figured that out in the previous section. And so we look at the tug of war that's set up, and we know that the net force is going to be the winning force minus the losing force. The net force we already know is 2. BC is what we'd like to find, and AB we know is 3. When we solve for the tension in BC, we find that it must be 5 newtons. So now we know that the tension in AB is 3 newtons, the tension in BC is 5 newtons, and we can check our work by going back up and looking at block C, the last block in the line. It is stuck in this tug of war between my 6 newtons of pull and the tension in BC, which we found to be 5 newtons. In that case, the net force is just 1 newton, which is what I had previously figured out. So going back to the original drawing, we can see that this 6 newtons will pull a 6 kilogram mass with 1 meter per second squared of acceleration. 5 newtons of tension here will hold this back against 6 newtons, giving it 1 newton of net force. That 5 newtons will accelerate this system of AB, which is 5 kilograms with 1 meter per second squared. 5 newtons pulling on B, 3 newtons pulling back, gives a net force of 2 newtons on 2 kilograms, which is 1 meter per second squared of acceleration. And then the 3 newtons here with no force pulling back on 3 kilograms, again 1 meter per second squared of acceleration. So everything moves in the same way.